Chapter 3 is entitled Shortcuts to Differentiation. And the key to achieving success in this chapter is not just by understanding the various rules and identities, but rather having the ability to recognize how you are going to differentiate the function you are presented with. So now let's dive into the content. In the first section, we're learning about the power rule. So instead of the last chapter where we had to do derivative by definition, like the limit process, now we have the specific rule that we can do it in seconds. So the formula the book gives us is y equals n times x to the n minus 1. So let's look at this as an example. So we have y equals x squared. So we'd rewrite that as y prime equals n, which is 2 in this problem, x to the 2 minus 1, which would become 2x. Let's look at some more examples. So we have y equals x to the negative fifth. That becomes negative 5, x to the negative 5 minus 1, which becomes negative 5, x to the negative 6. So the next example, 2x to the cubed. Right, so they become 6x squared. But this is the next one, y equals 2. To find the derivative of that, it's just a rule. Whenever you have a constant, it just becomes 0. And then the last one, y equals x, would just be 1. Alright, let's look at a problem that utilizes the power rule. So it states, find the equation of the tangent line when f of x equals negative x cubed plus 2x plus 1 when x equals 1. So the first step is we're given half of the point, x equals 1. Well, we want to find the full point. So what we're going to do is plug 1 into our function. So we're going to do that. And we're going to find our other point, which is 2. So now I have 1 point, 1 comma 2. But to find the equation of the line, we need a point and the slope. So to find the slope, we're going to find the derivative using our power rule. So, looking at the function, we have negative 3x squared plus 2. Now to find the slope, we'll plug in the point that they gave us, 1, and we should get the slope. So now we know the slope is a negative 1. So now we have our point and slope, and we're going to use our point-slope formula, plug it in, and hopefully get our answer. So we have y minus, or y2 equals negative x minus 1, and this will go to y equals negative x plus 3 as our final answer. That's the equation of the tangent line. Alright, let's look at a word problem. A ball is dropped from the top of the Empire State Building. The height y of the ball above the ground is in feet, is given as a function of time in seconds by this equation. So the first thing we need to find is the velocity of the ball at time t. So it does not give us a specific time, but it wants to find us a t. So the first thing we need to understand is this concept. When we're given a position function, which we are, the first derivative represents the velocity and the second derivative is the acceleration. This is extremely important as applied to almost every word problem. So using this concept we just learned, we take the first derivative, because we want the velocity, it'll be 32t. And obviously the sign is negative because the ball is falling down. Now let's look at part 2. When and how fast does the ball hit the ground? Give the answers in miles per hour. Okay, that's going to be a little bit of pain because it's originally in seconds per feet per second. But we're given a conversion factor here. So let's start this problem. But first, let's do the first part is when will it be. So that's when time equals 0. Looking at our first equation. So 0 equals this. I'm just going to solve. Isolate t. So when we do this, and you're going to be using your calculator to do this, you're not going to be doing it in your head. And it'll be about 8.84 seconds. So that's when the ball hits the ground because its time equals 0. But now we need to know how fast. So since we want to find velocity, we're going to look at our second derivative, which we found in the part A, which was negative 32t. So now we're going to plug in our time that we found over here into here. So 8.84. And we're going to find that this equals about negative 282.88 feet per second. But remember, we want it in miles per hour. So to do this, we're going to take the answer we just got and multiply it by our conversion factor, which is negative 192.85 miles per hour. All right, let's look at another word problem. The demand curve for a product is given by Q equals 300 minus 3P, where P is the price and Q is the quantity that consumers want to buy at this price. So first wants us to write revenue as a function of RP of price. But before we do that, we need to understand that revenue equals the quantity times the price. This is something you have to memorize. So we're going to apply this right here. We know that our quantity is 300 minus 3P, and our price is just P because it's not given. And we're just going to distribute, so we get 300P minus 3P squared. So that's the answer to the first part of the question. The second part is it wants to know what prices of R prime of P are positive and or negative. So before we do anything about the positive or negative, we first just need to find the first derivative. So to do this, we're going to do power rule 6P. And now, to know when it's positive or negative, we know that something is positive when it is greater than 0. So basically that means when this is greater than 0, it's positive, and it's negative when the first derivative is less than 0. And now we're just going to solve for P. But be careful of which way the inequality is facing. So if 300 greater than 6P, I like to always have the variables on the left side, and that'll flip the inequality, and we'll isolate P to find it's less than 50. Now over here, we have 300 less than 6P. We'll flip it to get the variables on the left side. We'll find P is greater than 50 when it's negative. So we now can answer the question. When P is less than 50, we know it's positive. And when P is greater than 50, we know it's negative. The second section is about exponential and logarithmic functions. So the first rule is that when f of x equals a to the x, the first derivative is natural log of a times a to the x. This is just something you need to memorize. So let's look at this in application. F of x equals 3 to the x, using what we learned above. The first derivative would equal natural log of 3 times 3 to the x. Let's look at some more of the rules that come from this rule. So the first is when the derivative of e to the x is just e to the x. However, when we have a constant with the x, the constant also comes out in the front when there's a derivative. So look at an example. So f prime of x would be 2 times 3, so 6 e to the 3x. Now let's look at some more complicated examples. But before we do that, there's still one more rule that we need to learn about. It's the derivative of a natural log, which is 1 over x. But I like to think of it as 1 over x multiplied by the derivative of x. And you'll see so in the next problem. So let's apply this rule. We're going to take the first derivative. So we're going to do 1 over the whole bottom, x squared plus 1, multiplied by the derivative of this, which is 2x plus 0, so 2x. We're going to multiply these two terms together to get one fraction, and we have our answer. Let's look at one more example. So we have f prime of x, 1 over the inside, which is 5x, multiplied by the derivative, which is 5, which becomes 5 over 5x. But be careful, this just becomes 1 over x. But do not be confused that you got it wrong, because it is truly 1 over x, even though it looks a lot like this. And let's do a couple more problems for quick practice. So we have f of x equals x squared minus 2 natural log of x. So we're going to take the first derivative of this. So the first part is just power rule. So bring out the 2 out front. We have 2x, then minus, the 2 is just a constant, so it stays out there, over x, which is 1 over x. Alright, let's do the next one. So we're going to say f prime of x equals 5, which is just a constant, so we're going to leave alone, times the natural log of 2 times 2 to the x minus 5 plus 0. Alright, let's look at the last one. But before we do that, we need to rewrite this. So we're going to rewrite the function. The first part's fine, 2 to the x. We can take the derivative of that. We can't do the second part, so we have to write as 2x to the negative 3. So now we can take the derivative. The first part, do natural log of 2, the base, times 2 to the x. And then the next one is power rule. So we have 2 times negative 3, which is negative 6. X negative 3 minus 1, negative 4. Alright, let's look at one last problem for this section. Find the equation of the tangent line of y equals 9 to the x when x equals 1. So this is very similar to the problem we did earlier. So the first part we need to do is find the point when x equals 1. So to do this, we plug 1 into our equation, and we find it equals 9. So we have the point 1 comma 9. But to find the equation of a line, we need a point and a slope. So to find the slope, the first thing we're going to do is take the derivative, and that is going to be natural log of the base, which is 9 times 9 to the x. And we're going to plug in 1 to the first derivative to find the slope when x equals 1. And we'll punch this in our calculator and see it gives us 19.8, about that. So now our last part, we have our point, we have our slope, and we can plug this into y, our slope, point slope. Y minus y1 equals m, x minus x1. So y minus 9 equals 19.8, x minus 1. And we'll rewrite this, simplify, as 19.8, x minus 10.8. That's the equation of the tangent line when x equals 1. Alright, section 3.3 is about the chain rule. During the whole section, it's another method of taking the derivative of more complex functions. So before we dive into the chain rule, let's look at one more example of the power rule right here. So we have f prime of x equals, take a 3 out front, 3x to 3 minus 1, which is 2. So this would be the derivative. Let's look at it in this one. So we have f prime of x equals, so for this we're going to take our 3 out front, just like we do in the power rule. We're just going to treat all this just like one variable. And then this we're just going to do 3 minus 1, which we get 2. But what's new now is we take the derivative of the inside. So that would be 2x plus 0. But we're not done. We need to simplify. So we're going to multiply these two together to get 6x, x squared plus 1 squared. So the big concept in this is that you're basically taking the derivative of the outside times the derivative of the inside. Alright, let's look at one more. So we have f of x equals the quantity of x cubed plus 2x to the 10th. So to find the first derivative, we're just going to treat this just like one variable at first. So we'll take out the 10 out front, so we have 10 times the whole inside, then 10 minus 1, which is 9, times the derivative of the inside of both terms. So x cubed would go to 3x squared, and 2x would go to 2. And then we're going to multiply these two terms together to simplify. And then we'll get 30x squared plus 20 times the quantity of x cubed plus 2x to the 9th. Let's look at one more example. This one was actually in the last section, but we're just going to do it one more time because it is truly a chain rule question. But before we do, remember that the natural log of x, the derivative of that is just 1 over x. So just like before, we're going to take the derivative of the outside, treating this just as one variable. So we have 1 over the whole inside, 3x plus 2. And we're now taking the derivative of the inside, which goes to 3x goes to 3, and 2 goes to 0. Now we're just going to multiply these two terms together, and we get 3 over 3x plus 2 as our first derivative. Alright, let's look at some examples of taking the derivative using chain rule when we have e as a base. So before we dive into the first example, we need to remember that the derivative of e to the x is just e to the x. So now let's use this in application. So to take the first derivative, we're just going to keep the first part, because e to the x, the derivative is just e to the x, keep the first part the same. The second part, we're just going to take the derivative of this, 5x, using power rule, goes just to 5. And we're going to rewrite this and simplify just to make it look a little nicer. This e 5e to the 5x. Now look at the second example. So, to take the first derivative, just like before, it's originally all the same. And then we just multiply it by the derivative of up here. So it'd be negative 2x. And then we're just going to rewrite this as negative 2x to the e to the x squared. Alright, let's look at another problem. So we're given that y equals f of x, where f of 1 equals 2, and f prime of 1 equals 7. And they want to find f prime of 1, given the g of x equals the square root of f of x. Alright, so before we even try to contemplate what this problem is saying, we're going to rewrite g of x. So we're going to say g of x equals f of x to the 1/2. This is just going to be easier when taking the chain rule derivative, because with the square root it makes it a little harder. So now we're going to find the derivative of g of x, because we know g of x equals this. So this is where we use our chain rule. So we bring it to 1/2 out front. We're going to multiply it by f of x, and then 1/2 minus 1 is negative 1/2. Then times the derivative of the inside, which is f prime of x. So now we're going to simplify this to make it a little more easier to understand again. Take f prime of x, and then we're going to go bring this down to the denominator. So we have 2 times f of x, and then since it was negative originally, it's now going to be positive because we brought it to the denominator. Sorry. So now we're at the final step. We can plug in 1 to find g prime of 1. So f prime of 1 over 2 times f of 1 to the 1/2. So now we're going to look up here to find our values. So f prime of 1 is 7. 2 times f of 1, which you know is 2, to the 1/2. And now we're just going to simplify one last time to get our final answer of 7 over 2 root 2. The last section of the chapter is about the product and quotient rules. These are 2 more ways of taking a derivative, and they're specific to when either 2 functions are being multiplied together or being divided. So let's first take a look at the product rule. The book gives us this rule. When 2 functions are being multiplied together and you want to find the derivative, you take the derivative of the first times just the second function plus the first function times the derivative of the second. So now let's look at this in application. It's given to us 2 functions, f of x equals x and g of x equals x squared. So once let's find the derivative when they're multiplied together. So looking above, we're first just going to rewrite the rule with terms of what we're given. So we're going to take the derivative of the first times the second plus the first normal function times the derivative of the second function. So now, before we plug in our numbers, we first need to find the derivatives over here. And I highly recommend not doing this in your head, but writing it out. It'll definitely minimize your mistakes on the test. So now we have all the components we need, and we can plug them directly into the equation we created to find the first derivative. So f prime of x, we know over here, equals 1. We're going to multiply that by g of x, which you know is x squared, plus f of x, which is x, times g prime of x, which is 2x. So now we're going to simplify, and we can simplify one more time because both of these have the same power. So we get 3x squared. That's our final answer. Alright, let's look at one more example of the product rule, but this one will be a little more complicated. Because when we're finding the derivative of this function, you're going to notice that we have 2 rules we have to apply. Not just the product rule, but the chain rule and the product rule. So, like before, we always take the derivative of the outside, then the derivative of the inside. So what this means, alright, f prime of x equals, we're going to bring the 9 out front. We're going to write the whole inside, x e to the 9x plus e to the 6x, all to the 9 minus 1, so the 8th power. Now we need to find the derivative of the entire inside. So to do this, we're going to first identify that this is a product rule. So we're going to rewrite. Before we do that, we need to remember the formula that we were given in the last section. So we're going to apply this, and we're going to say f of x equals x, g of x equals e to the 9x, and then we're just going to try to find the derivative when these two are multiplied together. So we know that fg prime equals, so the derivative f of x, which is 1, then just g, so e to the 9x, plus just f, which is x, and then the derivative of g of x, which is, we bring the 9 out front, the derivative of the exponent, which is 9, then e to the 9x. We're going to simplify this as e to the 9x plus 9x e to the 9x. So remember, this is the first part of the derivative right here. So we're going to write this right here. But then remember, we have this derivative as well. So we're going to bring that 6 out front. And e to the 6x as our final answer. This whole function is a derivative. Alright, now let's look at the second rule for the section, the quotient rule. So this is basically when two functions are being divided by each other, and we need to find the derivative. So the book gives us this formula that's very similar to the product rule. We take f prime multiplied by g minus f times g prime all over g squared. But I have a little mnemonic I like to memorize this with. So I think low d high minus high d low all over the square of what's below. So what this basically means is low is basically the bottom of the function. So g high, d high means the derivative of the top, which is f prime, minus high, which is just f, minus d low, the derivative of the bottom, all over the square of what's below. So low d high minus high d low all over the square of what's below. This may not work for you, but it does work for a lot of people, so I thought I'd share it. Alright, now let's look at an example. So it's asking us to find the first derivative when f of x equals a quantity of 2x plus 1 over the quantity of x minus 3. So looking above, we're basically going to plug this into our formula. So the first derivative equals the derivative of the top times the bottom, the denominator, minus the top times the derivative of the bottom, which is 1, all over the square of the entire denominator. So now we're just going to simplify. So we're going to distribute the 2. Get 2x minus 6. Distribute the negative. 2x minus 1. And all over x minus 3 quantity squared. We can simplify the numerator a little bit further to negative 7 over x minus 3 squared as our final answer. In conclusion of Chapter 3, Section 1 talked about taking derivatives using the power rule for functions like 3x squared. Section 2 talked about taking the derivative when there's exponential or logarithmic functions, like e to the 2x or natural log of 2x. In the third section, we talked about chain rule, so finding the derivative functions like this. And then in the last section, we talked about product and quotient functions, when two functions are being multiplied together or being divided. And in the end, what makes this chapter difficult is not understanding how to take each of these derivatives, but identifying what method you're going to use on the test. Because it's not going to say find the derivative using chain rule. It's just going to say find the derivative. Then additionally, the derivative that you need to find may incorporate different rules, like two rules in one. So what I really recommend is doing practice of various derivatives and mixing up the problems, as not knowing that you're going to have to use a chain rule on this one and the exponential rule on this one, but doing a mix so you recognize the problems when you get on the test. And I thank you for watching this video, and best of luck.